We have 3 different ways to get the frequencies of amino acids. What are 3 different ways to get the frequencies? Unweighted frequencies, weighted frequencies and independent counts, right. So, fine. Now, if you got the frequencies, we need to convert these frequencies into score, right. So, for example, if we have this sequence, okay, this position. So, what is the frequency of G at position number 60? 10 by 10, right. So, this is equal to 1. If we take this position number 9, so if you see there, what is the frequency of these amino acid residues? How many times T occurs? T occurs 7 times, alanine 1 time, glycine 1 time, serine 1 time, right. So, now convert this into frequencies, right. The frequency of threonine at position 9, this is equal to 7 by 10, this is equal to 0.7. So, frequency of alanine at position number 9 equal to 0.1, right, and the frequency of glycine at position number 9, this is equal to 0.1, as well as frequency of serine at position number 9 is equal to 0.1, right, to get the numbers. So, now we convert these frequencies into scores. So, for first we do the entropy based score. So, here if you see this frequency, right, any position I of any specific amino acids, if a specific position is occupied by a single amino acid, right, you will get this FEI that is equal to 1, right. If it is occupied by different amino acid residues, FEI will be different depending upon the number of times each amino acid residue, right, occurs at particular position. If they are randomly distributed, then the frequency will be 0.05, right. So, you will get 0.05 as the frequency. Then the frequency we multiply with the logarithmic of this frequency, right, to get the conservation score based on the entropy based method. Here is not biased with amino acid composition or similarities among amino acids, because we do not give any bias for the similarity of amino acids. If it is 7, 2, 2 for the 3 different amino acids present at a position, it does not matter if it is 7 is threonine or 7 is alanine or 7 is tryptophan, right. We do not give any weight for any of the amino acids. And there is another method that is called variance based method. So, here this will consider the frequency of amino acids, same amino acid at different positions. For example, here if you see the sequence, the same amino acids located at different positions. For example, if you see glycine here and we have glycine here and glycine here, and some cases it is highly conserved and some cases with variable residues, and look at the other residues, how far they are variable. So, they compare how many positions glycine occurs, how many positions they have similar residues, and what is the proportion of these residues, they take into consideration when you calculate a score. Right. Now, the equation is FEI, this is the frequency of amino acid A, right, in the alignment, and they take the overall frequency, that is FEI, overall frequency of this amino acid A in the alignment. So, then compare this with any particular positions and then use this equation FEI minus FEI, right, take the square and finally summation over all the pairs and then take the square root, then we will get this conservation score. Here the frequency either we use weighted ones or they use the unweighted ones. If you use unweighted ones, then you get this the equation. So, NFI divided by sigma NFI n I equal to 1 to L, or this is the number of aligned positions, this for unweighted. If you want to go with the weighted ones, then we give the weightage delta A comma k comma I, depending upon the weightage you can give this equal to 1 or this equal to 0. So, what are the advantages of having weightage? So, here the overall amino acid frequencies which differ from different families. So, if you want to implement, if you want to include this information, then we need to give weightage for the different protein families, then we can see which one is highly conserved compared with the other ones. Then there is another measure, this is called sum of pairs method, right. Here if you have these sequences you are aligned FEI and FBFI, then we give the scoring matrix depending upon the aligned residues. So, which scoring matrix we use, we discussed about 2 matrices, either PAM matrix or Blossom matrix. So, we use these numbers A comma B, right, where A equal to 1 to 20 and B also varies from 1 to 20. So, we use any scoring matrix and then we give the weightage based on these aligned positions and you can calculate the score, right. So, this also depends upon the amino acid type. If the conserved position not the same residues, if similar residues are present, then we get high score, right. So, the value will be high if the positions are occupied by similar amino acids. If it is completely different amino acids like lysine and alanine, then you will get less score compared with the similar amino acids like lysine and arginine. So, this is why we get the sum of pairs method. Okay, now we will see how to obtain the values. So, this is the one example. I give two different positions. Position number 3, if we take position number 3, it is occupied by leucine, right. I will show the sequence, right. If you take the position number 3, this position, what is the frequency of residues at position number 3?
10 by 10.
This is occupied by leucine, right, leucine 10 times. If you take the position number 6, alanine 8 times, D 1 time, E 1 time. So, now we get the frequency. So, f of A equal to 0.8, f of D this is equal to 0.1 and f of E this is equal to 0.1. So, if we take position number 3 occupied only by leucine and the preference is 10 by 10 this is equal to 1. Now, we convert these frequencies into score. So, if we take the entropy based method, so C of I the score 1 into logarithmic of 1, right, this is equal to 0. If you take the position number 6, right, the equation is f of I into logarithmic of f of I, right, I varies from I equal to 1 to 20. So, here we have only 3 amino acids, right, because 3 residues, one is the 0.8, one is 0.1 and the 0.1. So, now conservation score we calculate, okay, this is the equation, okay, this is the equation, right, 0.8 in logarithm of 0.8, 0.1 logarithm of 0.1 and 0.1 logarithm of 0.1, right, this is equal to 0.8 into this is logarithmic values, we substitute the numbers and finally we get the conservation score of 0.638. If 20 different amino acids are distributed randomly, then what will be the distribution, what will be the score? 0.05, right, 0.05 for one amino acid, 0.05 into logarithmic of 0.05. We will get how many times? 20 times we get. So, multiplied by 20. So, what is logarithmic of 0.05? You get the numbers and multiplied by 0.05 and get it multiplied by 20, then you get the numbers. If you compare these two values, for example, this is 0 and this is 0.638, which one is conserved? 0. It is conserved, right, because if you have all the positions occupied by the same residue, then it is highly conserved. So, you can get the 0, but here this goes the negative values. If it is highly variable, then it is going less because it will get more negative values. Now, you can normalize these numbers, because here we get the numbers maximum of 0 and minimum numbers. So, you can normalize, we can normalize using the equation, right, see normalization of I for new positions, this is equal to C of I, right, consideration of a particular residue, right, C of I minus mean of C, that is C prime, this is equal to summation C of I by n, I equal to 1 to n, number of sequences aligned in this position, right, and sigma. What is sigma? Standard deviation. How to get the standard deviation? This is equal to C of I minus mean of the C, right. So, then we divided by the square, right, and finally get the 0.5. This is not square root, right, square, the C is confused, so this is C. So, C of I minus C average, you have to square it, right, divide by n minus 1 and take the square root, right, you will get this deviation. So, we will use the C of I minus C average divided by sigma, then you will get the normalization. In this case, you will get the numbers, right, normalized with this respect to 1. So, you get the negative values or the positive values, right, with respect to this 1. So, now this is the method you can calculate the conservation score, and we have several algorithms available to get the score based on all these methods. For example, one of the publicly available method is AL2CO, there is alignment to conservation. This accepts the multiple sequence alignment in cluster format. What is cluster format?
identifier and then sequence.
Right, this is identifier and the sequence. It is the program for multiple sequence alignment. If we give the single sequences and if align using cluster, then you will get the output. This is the identifier. This is the UniProt code, UniProt ID, and here you give the sequence. So, if we give this one, and there are various ways you can select. This is what we discussed. We discussed about the different frequencies, either we use independent count or you use unweighted or you weighted, and the conservation score we have different ways. You can use entropy based method and the variance based method and the sum of pairs method. We discussed one example based on unweighted frequency and entropy based method. So, just for the verification I put unweighted frequency and the entropy based method. So, here this is the website you can get the AL2CO method to get the conservation. So, if you click, if you give the submit button, you will get the data, right, which is asking for the positional conservation or the alignment with the integer conservation, right, we will get the values, or you can classify into different groups, different numbers. So, if you want to check your input, this is input alignment is here. If you click on here, you will get the input alignment, or you can get the positional conservation here. If you go with the positional conservation, okay, these are the different amino acid residues. We discussed about few positions. So, remember which positions we discussed? 3. So, 3 is the value of illusion, right, we get 0, right, okay, here this is the value we get is equal to 0. So, it matches with the number. So, you can see 3 this is equal to 0. Then we check the position number 6, that is alanine, right. If with the position number 6 we checked the values, we get minus 0.638, here also if you see in this program we get minus 0.639. Then we check position number 9, so this is equal to minus 0.940, because that is more variable than the position number 6. So, just I show the sequence. If you see position number 1, 3 is highly conserved, 60 is conserved, and position number 6, that is 8 plus 1 plus 1, and position number 9, 7 plus 1 plus 1 plus 1. So, it is more variable. So, if you look into the answers, so you can see the distribution of these residues based on conservation, right. You can see this is 0, highest one, and 6 is variable, and 9 is again is more variable, right. So, you can see the numbers. So, you can get the numbers into normalized one as I discussed earlier. So, this is a normalized one, you can use this equation to normalize the scores and look at the normalized values. So, this is the data which we obtained with the weighted matrix. If you use the weighted matrix, right, if you see here the weighted method, right, we will get these numbers. But if you compare these two, if you have a similar set of sequences, because in this case we use 10 sequences, they are from the similar sequences, right, similar family of sequences. This is why if you see there is a good correlation between this number and this number, zeros, 0.9, 0.9, 0.6, but here 0.8, you can see the correlation between the unweighted and the weighted frequencies. If you use completely different sequences, then you can see a difference between the score obtained with the weighted frequencies as well as the unweighted frequencies. So, now the next aspect is we get some numbers, right. So, here we get several numbers 0.00, minus 0.94, minus 0.63 and so on. How to convert into numerical scale, because here we get sequence. For each sequence we need to assign some numbers. So, I want to do it between 0 and 9. If you see this highly conserved is 9, right, 9 is highly conserved, and to see the variable it is 0, then they automatically normalize and put the numbers for each sequence. This is the query sequence. So, we take this as the query 1, and for this one they put the numbers here, these are the places where it is highly conserved, and here these are the region it is very highly variable, right. You can see the numbers, and these numbers you can use as your input for several prediction algorithms that we will discuss in the later classes. This is one method. Then there are several methods which can calculate the conservation score, right, because why we are concerned about conservation score? This will give you the structural important positions, this will give you the functional important positions, and these positions they try to maintain in different sequences, means if you alter these residues it will have adverse effects. So, this is the reason why the conservation score is one of the features, right, for the predictions. Second aspect, to calculate the conservation score we do not need any structure information, we need only the sequence information. If you give the information regarding homologous sequences, you can calculate the conservation score from the sequence, right. Getting sequence information, that is easy because we can have more number of sequences than structures, right. How many sequences in the UniProt database now? 78 million sequences. So, you get more number of sequences. So, even if you have homologous sequences, you get sufficient number of sequences for the conservation. Approximately how many sequences are required to calculate the conservation score?
More than 2.
Right. If you get 3 sequences, you can get the conservation, but is it reliable or not? No, right. So, if you get the reliable values, so at least we need to have more than 100 sequences. If you have more number of sequences, we can see the variability. If you have less number of sequences, right, now we discussed with 10 sequences, many positions here we get the same residues. Here if you, this is the sequence I gave, only 10 sequences, and if you see G is same at 60 and same at this position, right, and you see H is same in the position 59, it is mainly because less number of sequences. If you go through 100 sequences, the probability of glycine in all the 100 sequences is very less compared to the probability of glycine in the 10 sequences, right. So, if you go with more number of sequences, even if you take 100 sequences and all the 100 sequences, if glycine occupies at 6th position, then your data are significant. You can say that glycine is very important at position number 60, right. So, in this case, to make sure, right, for the reliability of your results, so you should have at least 100 sequences for calculating the conservation score. So, we discussed about AL to CO. So, now there is another method, this is called conserve. So, here it is easy to do that, we do not have to give any sequences. If the structure is known, right, you can give just the PDB ID. If we give the identifier of the protein data bank, I will discuss about the protein data bank in later classes, right. So, then automatically this will get the sequence mapped to the PDB and it will get the homologous sequences from the UniProt database and they do the multiple sequence alignment and finally get the score. In the case of AL to CO, what is the input? Multiple sequence alignment. So, you have to work, take your sequence and get the similar sequence homologous sequences and you have to do the alignment and you have to give the multiple sequence alignment as the input. In this case, if you give your PDB ID, it will automatically get the sequence, right, and find the homologous sequences, right, and then align the sequences, get the multiple sequence alignment and finally you will get the data. So, it is very simple, just to give the ID, but there are several issues. If your PDB ID or if your sequence, it does not have sufficient number of homologous sequences, you do not get any results, it will get, you cannot calculate the conservation. But in the case of AL to CO, you know that how many sequences you get, be depending upon the sequences, if you give, you will get the results. That is the difference between using different servers. So, if you give this ID, so it gets the sequence from UniProt, right, from this database you get the sequences and then finally it aligned. From this one you can see different colors. This is also easy to identify the residues which are highly conserved or which are highly variable, right. If you see these colors, so can you see which residues are highly conserved, which color? Magenta. If you see this one, right, this is L, right, if you see this is T, this is a dark, right. So, dark color you can see these residues are highly conserved. Easily if you see this picture, you can see that there is residues which are highly conserved and some cases it is highly variable. For example, if you see this one is occupied with leucine, glutamic acid, threonine, aspartic acid and valine, right. There are various residues occupies at this particular position. So, this will clearly tell you which residues are conserved and which residues are variable. Then we give the text file, this will give complete details. Okay, here this is your sequence. So, here this is the atom in the PDB file and this is normalized score and here they give the color code. So, color code they put the conservation as 9 and variable as 1. So, numbers vary from 1 to 9, 9 is for conserved and 1 is for the variable. This is the position in the derived sequence. So, you can see the data. So, whether what is the variability, first one is mainly by lysine and the second lysine by lysine. So, that means highly conserved and the second one valine, this is occupied by different residues, isoleucine and lysine, threonine, valine. So, this is why the color code is 3, that means this is not conserved, this is variable. So, here this is occupied with lysine, so it's the color code is 9, so it is highly conserved. Likewise, if you see the same residues, so it is highly conserved, if there is only 2 residues, so this is the color is 8, right, it will be highly variable, right. So, you can see the color is 1. So, depending upon this variability they give color codes from 1 to 9, right, and then you can see which one is conserved and which residues are variable. Then make this figure, this is actual 3D structure, how the protein looks like, right. If we say different colors, right, can we see which positions or which location the residues are conserved and which positions they are highly variable?
Magenta color, sir.
If you look at this, okay, these regions, right, okay, you can see some of them which are interior, right, they are highly conserved mainly because the residues are preferred to form the hydrophobic core. So, interior seeking residues are mainly hydrophobic residues. So, the variability is only among the hydrophobic residues. So, they prefer to be highly conserved. Right. Some cases mainly in the case of the surface, right. So, you can see they are highly variable, they try to interact with other residues, right, maybe different types of interactions. In this case they have the variability to change the residues among the polar residues or charge residues and so on. So, when you have these 3D structures, then also you can see which regions are highly conserved and where are the variable regions, right. So, if we get the conservation, we will get a picture about from the sequence level, right, which residues maintain to have the same position, right, in any homologous sequences. So, we can summarize again. So, what did we discuss today? Conservation score, right. So, the conservation score means you get the sequentially similar positions, right, among the homologous sequences. The two steps, the first step is to get the frequency. What are the different ways to get the frequency? Unweighted frequency, weighted frequency and independent counts. To get the score, entropy based method, variance based method and sum of pairs method, you can get different scores, right. You can use any of these methods, right, to get the score. So, what are different algorithms we discussed? Online sources, AL2CO, there is algorithm to conservation. What is input required for the AL2CO? Multiple sequence alignment. So, what is another program we discussed? Conserve. What is the input for this conserve? PDB-ID. Right? Also, it is also possible to give your sequences or the alignment, right, in the conserve also to get the conservation score. So, finally, they give the numbers, right, from the variable to the conserved, right, maximum 9 they give and the minimum they give 0 or 1. So, you can see in the PDB where you can see the conserved regions or where you have the flexible regions. So, in the next class then we will extend it, right, to see the how to construct phylogenetic trees, right. If we have the multiple sequence alignment, how far the sequence are similar to each other, whether 1 and 3 are similar or 1 and 5 are similar or 2 and 3 are similar, right. So, based on these variabilities we will try to construct trees. From the tree construction we will see what are the residues or which are the sequences, right, which are similar to each other, which are closely related to each other and so on. Thank you for your kind attention.